Hello, everybody. Hey, this video is on problem set 2 help from week 2. And I apologize for not getting this out earlier, but as some of you have realized, either being in class or on Zoom, I had a really hard time with 54, and I seemingly had the right answer, but then when I went to the check, it did not work. So I am actually still working on that. I am going to go over my logic on that and in this video at the end. So if you just show me the work that you have done on 54, or if you had no clue where to start, then you can look at what I did, write it down, and submit that. But maybe you will see the error that I am making on 54, but we'll see. But just so that we get a little bit of stuff in here, these are obviously our answers over here, which all of them except 54 were in the back of the book. But we're going to quickly do 39. And in problem 39, it says a student throws a set of keys vertically upward to her sorority sister who is at a window 4 meters above. The keys are caught 1.5 seconds later by the sister's outstretched hand. With what initial velocity did were the keys thrown? And what was the velocity of the keys just before they were caught? So as is the case, we want to figure out what we're being asked for, and that is obviously the initial speed that they were thrown and then the final speed that they were caught. And we want to also write down what variables that we know and draw a picture. So we're basically going to have kind of like a balcony sort of here, and then we have a sister kind of, let's see, sister throwing it up. Okay, so we do not know the initial speed. We do know the height, and we're going to call that delta y is equal to 4. The delta y is equal to 4. Our time is equal to 1.5. And the hidden one in there is that our acceleration is negative 9.8. Okay. So if we look at this variables and we are looking for the final velocity, we are going to be using the kinematic equation number 3, which is going to be delta y is equal to a VIT plus 1/2 AT squared. And we have all the information except for the initial velocity. So we're going to say delta y minus 1/2 AT squared is equal to VIT. And then we're going to subtract or divide by t, and we're going to get our initial velocity. So we have 4 here minus 4.9 times 1.5 squared divided by 1.5, and that should give us the velocity. So we're going to have 1.5 squared times negative 4.9 equals, actually, this was a negative, and when we moved it to the other side, it turned positive. So that is going to give us 15.05, and we're going to divide that by 1.5, and we're going to get this initial velocity that's equal to 10 meters per second, and that's positive. So that is going up. So that is our answer to part A. And in our answer to part B, okay, we are looking for the final velocity. And so we can say V final is equal to V initial plus AT. We now know our initial velocity is 10. We know we have 9.8 times 1.5, and that will give us V final. So we're going to say 10 minus 9.8 times 1.5, and that is going to give us negative 4.7 meters per second, negative 4.7 meters per second. And that's going to be our V final. Okay, so that is problem 39. Okay, now you guys, that is really going to bring up problem 54. Okay, now again, like I said, problem 54 is going to be ones that I came up with an answer, but it did not check out when we plugged in numbers. So I am going to kind of review that with you. You guys can check my logic, and in the very least that you can write down what I'm writing down as far as showing your work. And if you just show me that work, even without an answer, that is going to count for your homework submission. So just as before, it is good to write down all of the given values, which I will kind of put in there as we go, and also to draw a picture. So obviously, if you've done this problem, you've got a car going at the speed limit, and it is approaching an intersection that is 22 meters wide. And then the light goes yellow. So how long should the yellow light be on in order for the person to react and stop before the intersection, or just continue at the same speed and go all the way through the intersection? Okay. Now, I think if we draw some graphs to kind of help us visualize it as opposed to a picture, it might help. So on the position versus time graph, okay, we're going to have just the car moving at a constant velocity. So and a constant velocity on a position versus time graph is going to be a straight diagonal line, in which the slope of that line is going to equal to its velocity. And then you also are going to have a, for the first 0.6 seconds, those two lines are going to coincide because they're both moving at a constant velocity. The 0.6 seconds is the reaction time, at which point the car is going to slow down at a constant deceleration of negative 2.4 meters per second squared. So you guys remember, on a position versus time graph, a constant acceleration is going to be a parabola. It's going to be a curved line. Constant velocity, it's going to end up having a parabolic shape, but we're only using part of that parabolic shape. So now when we get into the distances, so from here all the way through would be what I'm calling x plus our 22 meters, and so that means that the car that's going through the intersection at a constant velocity is going to go all the way through, yet the car that is going to react and then slow down is going to go 22 meters less, or just x. Okay, now that is one way to look at it. Another way to look at it is on a velocity versus time graph. And in that velocity versus time graph, we're going to have a constant velocity, which is going to be a horizontal line. And that's going to be our VO. Now, just that v naught, which was given in the problem, is the same thing as the initial velocity. Okay, so what's going to happen is this car is just going to go at that particular speed, and it's going to go right through. Now, at this time, okay, whatever the total time is, it will have gone this distance. Okay, now remember, if you calculate the area under a curve for a velocity versus time graph, it's going to give you the displacement or the distance. So if we have the time total, okay, that would be this whole distance, and this whole area is going to be x plus 22. Now, the car that is going to react and slow down is going to first have the same distance for 0.6, or the same velocity for 0.6 seconds. At which point it is going to slow down until it reaches a stop. So, and I did lots and lots of different methods to do this, and was banging my head against the wall. But what I ended up concentrating on was just this triangle right there. Okay, now remember, that's decelerating, so it's on this velocity versus time graph, it's going to have a straight diagonal line, but the slope is going to be negative. And this slope right here is going to be negative 2.4. Okay, so now I am going to call the time, I'm going to call this time t, okay, and I'm going to call that t1. That is not the total time. That is not the total time, okay? And so in order to calculate displacement, we're going to have, well, actually, we're going to use kinematic equation number 2, which is V final is equal to V initial plus AT. Now we know that this initial velocity was 0, and we know that this initial, we know the final velocity is 0 because it stopped. We know the initial velocity is V naught. That's just because what they called it. And now we're going to have minus AT because that acceleration was negative. Okay, and we know that that was negative 2.4. So we're going to subtract V naught and divide by negative A, which is 2.4. And that right there, the negatives cancel out. That right there is equal to the time. Okay, but remember, that was only the time for here. Okay, and so in order to get the full time, we're going to add 0.6. So we're going to have VO divided by 2.4. Okay. And that if we add 0.6, that is going to be the total time. Okay. So this essentially right there is giving us part A. Now in part B, they're asking you to plug in your different velocities, and in the first case it was 8 meters. Okay, so now if we are going to calculate the distance that the car moves in coming to a stop and compare that to the distance that the car goes without stopping and subtract 22 from that, they should be the same distances. Okay. All right. So I'm going to say for the car that stops, okay, we're going to have velocity times 0.6, right? And that is going to be this portion right there. And then the next portion is going to be kinematic equation number 3, which is delta x is equal to VIT minus 1/2 AT squared, or plus, but in this case it's minus. Okay, so we're going to say plus V naught T minus 1/2 AT squared. Now remember, this T right here is just this one, okay? And we will get back to this other one here in a second. So this should give us our delta x. So now if we put in 8 for this, we're going to have 8 times 0.6. And if we do this equation right here, we're going to have 8 divided by 2.4. And 8 divided by 2.4 is going to be 3.33. So T is equal to 3.3. So we're going to put in plus 8 times 3.33 minus 1.2. Now remember, our acceleration was 2.4. We're going to divide that in 2, and we get 1.2. And we're going to have 3.33 squared, and that should be the distance we travel, in coming to a stop. And that is going to be 8 times 0.6, which is 4.8. 8 times 3.333, which is going to be 26. We'll call it 7. And then we're going to say 3.33 squared times 1.2 is equal to 13.3. 13.3, that's minus. So we're going to take 4.8 plus 26.7 and 4.8, and we're going to get a displacement of 18.2. Okay, that is going to be our delta x. So now we're going to compare that. We're going to compare that with how far the car is going to go if it doesn't stop. Okay, and that is going to be the velocity initial times the total time, okay, which is going to be t plus 0.6, okay, but that is going to give us, that's going to give us x plus 22. So here we're going to subtract 22, and that should be the same delta x that this is. And if we put in 8 times 3.33 minus plus 0.6 minus 22, that is going to give us delta x. So we're going to say 8 times 3.33, times the quantity of 3.33 plus 0.6 equals 31.44 minus 22, and that gives us 9.44, which is not the same. And I have been driving myself crazy trying to figure this out, and I have not been able to do it. So if you've got that, to me, that seems completely logical, but it's obviously not coming out with the right answer. Now, I did some manipulations just through figuring out the numbers, and I ended up, if you had about 4.3 seconds, 4.3 seconds is equal to the time, then that would give you a value where they would come out to be the same distance. And I only did that for the 8 meters per second because I got so frustrated. So anyways, hopefully you guys had an insight or see an error that I did that you did not, and you guys can get back to me. Okay, that is week 2, problem set 2, help. And I hope that did help, even though we didn't get the right answer. All right, so we'll see you guys next time.